We're going to take a look at the fourth problem from the classical mechanics assessment test written by Professor Lay. So let's go ahead and open up a new document here. All right, the situation is as follows. We've got a wheel, and this wheel has spokes, and this wheel with spokes is going to be rotating freely. And importantly, there is a bug stuck on one of these spokes. So I've got my bug here. So obviously, as we said, the wheel is going to be rotating at some angular velocity omega, and I'm going to call this omega initial. And during this motion, as it's rotating initially at this angular velocity, this little bug here starts walking towards the center of the wheel on one of the spokes at a certain velocity. And initially, when it starts the motion, this bug is a distance r from the center of the wheel. So I'm going to say that this distance is going to be r. So he has a distance r from the wheel. We'll specify some other parameters. We'll say the mass of the wheel is m, and the radius of the wheel, one radius here, is rather half the diameter is the radius. It's going to be r. So we've got our value r here. And one of the questions is, once the bug gets to the center of the wheel, what's the new angular velocity going to be? Is it going to change? What's going on here? What does the physics say? So before we even look at the equations, we can say, naively, we can imagine this kind of like an ice skater, bringing her arms in closer and seeing what happens to her speed. And just intuitively know, as the ice skater brings in her arms, she's going to speed up her rotation. So we might think that as the bug approaches the center and gets to the center here, the angular velocity might increase. So that's kind of how we can visualize the situation. So first of all, we're going to identify our conservation equation, and in this case, we know that angular momentum is going to be conserved. So what I'm going to say is that we have our initial moment of inertia multiplied by, or rather our final moment of inertia multiplied by our final angular velocity, and this quantity has to be equal to our initial moment of inertia times our initial angular velocity. So this omega and this omega are the same, and we're trying to identify what's happening here. So from first principles, we can see that well, the moment of inertia is going down from initial case to final case. The bug is going to reach the center, and once the bug reaches the center, the total moment of inertia for the system is going to decrease. Specifically, we know that the final moment of inertia is going to be less than the initial moment of inertia. And because of this, we can also say that the final angular velocity is going to be greater than the initial angular velocity, kind of like the skater bringing arms in, spins a little bit faster. So that's kind of good, but that doesn't answer the question quantitatively. So we want to see how do we determine what the final angular velocity or moment of inertia is? What is the initial moment of inertia? Well, the initial moment of inertia, well, what is moment of inertia? Moment of inertia is nothing but the sum of the mass elements at whatever distance those elements are from the center of rotation. And let's get our subscripts right. So for the wheel, this is a pretty simple process. It's all the mass that's distributed, I should specify I wheel, all the mass that's distributed exactly a distance capital R away. So the moment of inertia of the wheel turns out just to be, well, it's capital M, it is mass M, and all of it is a radius R away, so this simplifies to just mr squared. So how about the moment of inertia of the bug itself? What's going on there? So we see that for the bug, it is also going to be distance r away, except in this case we have lowercase r, r squared, and we find that this is going to be equal to lowercase m times lowercase r squared. It is mass m. I should specify little mass m at a distance r away. So this would be the initial states of everything. We want to see kind of what's going on here. All right, let's give myself a little bit more room over here. Great. So what happens in the end? So in the beginning, rather, we have the wheel, moment of inertia of the wheel. We have the moment of inertia of the bug, and we want to see how these quantities are affecting the final angular velocity. So what's happening? Well, the bug. Let's see how the moment of inertia for the bug changes. In this case, the final moment of inertia, well, that's going to be the mass of the bug times the radius final squared minus the mass of the bug times the little r squared, the initial case. So this is the change of moment of inertia of the bug, and well, what is the final radius? Well, the question says the bug is going to the center of the wheel. So obviously the center, the 0 squared is still going to be 0, so we don't have any moment of inertia contribution from the beetle in the final case. So this is cool. What can we do with it? Well, what I'm going to do is I'm going to substitute it into our initial equation up here, our conservation equation, IF omega F equals II omega I, and let's see what we get. So let's rewrite this. I'm going to say IF omega F equals II omega I, and omega F was what the question asked about. What is the angular velocity doing? So let's solve for this, and I'm going to say that the final angular velocity is going to be equal to, so we have our ratio of moments of inertia, and so we've got our II divided by IF multiplied by omega initial, and immediately we can see something about this. We see that since our moment of inertia is going down, this quantity is going to always be greater than 1, which means that this omega initial will be multiplied by some factor greater than 1, which means this has to be larger than this, which is good. That's a good check for ourselves. So now, what do we do with our moments of inertia? Well, the final case, or rather, let's take a look at the initial case. Our initial moment of inertia is going to be nothing but the sums of the moments from the bug and the wheel. So in this case, we've got, I'll go ahead and write it. Our initial moment of inertia is going to be mr squared plus little m little r squared. And how about our final moment of inertia? What's going on there? So our final moment of inertia, this goes away. We don't have any more contribution from the bug. So our final moment of inertia, all we have left is just mr squared. So let's plug it in and see what we get. So we've got our omega final, and this is going to equal our omega initial, which is mr squared plus m little r squared divided by mr squared and multiplied by our initial angular velocity. Cool. So this, I guess this would kind of be a solution, but we can actually make another step to simplify. I'm going to take out our mr squared, divide both sides by that. So we've got, let's see, we can say omega final is going to equal, well, we've got mr squared over mr squared plus little m little r squared divided by capital M r squared. Cool. This is just 1. So that means, multiplied by omega initial, that means that our final angular velocity is just going to be equal to, well, 1 plus little m little r squared divided by big M big R squared times the initial angular velocity. And we can see much more directly that this is always going to be greater than this, at least for the physical situation set up by the problem, because it's 1 plus something. 1 plus anything not 0 is going to be greater than just 1, obviously. So there we get our final answer. And the second part of the question I will address later, the forces that the bug feels during its motion. We'll take a look at that momentarily.